In this video, we're going to take a look at proofs by induction. The logic behind them is expressed in the induction axiom, which states this. Okay. Let P of n be some proposition involving a positive integer n. I'll give you an example of that in a moment. Okay. Then the induction axiom is an if-then statement. It says if these two things are true, first, P of 1 is true. So the proposition is true if n happens to be 1. And second, the second part is itself an if-then statement. If P of k is true, then P of k plus 1 is true. So that if the statement is true in one case, then it follows it's going to be true in the next case as well. And if both of these things are true, the initial case is true, and we've got this if-then statement, then we can conclude that that proposition is true for all positive integers n. Just to give a quick example that's not particularly mathy, suppose I have an island, and on this island, all of the people happen to have blue eyes. Now, blue eyes is a recessive trait, so if people are reproducing, and they're only reproducing with other blue-eyed people, then all the children are going to have blue eyes. Okay. So, my proposition here might be the nth generation has blue eyes. So that's actually infinitely many statements in one, because I get one statement for each value that n can take on. So if n is 3, I'm saying the third generation has blue eyes. If n is 500, I'm saying the 500th generation has blue eyes. And to see that that's true, we would just establish that these two hypotheses are satisfied. So P of 1 is true because the first generation does have blue eyes. That was the given information. This says if P of k is true, then P of k plus 1 is true. So k here is going to represent a fixed but unspecified number. So we're saying suppose that some generation, the kth generation, has blue eyes. How do I know that the k plus first generation will? Well, because blue eyes are a recessive trait. So if the only people on the island all have blue eyes, then they're reproducing with other blue-eyed people. The next generation is going to have blue eyes. Now, of course, this is supposing that nobody comes in from the outside and that no gene mutations take place. But under those circumstances, the kth generation having blue eyes would force the k plus first to have blue eyes. So we can establish that these two things are satisfied, and then our conclusion is, oh, well, that means that every generation is going to have blue eyes. Okay. All right, so let's try an example that's a little bit more mathy. And we'll see how we can use this induction axiom to actually do a proof by induction. Okay. So, prove by induction that the sum as I goes from 1 to n of I is equal to n times n plus 1 over 2. So let's just do a quick review of what this notation means. This right here is a capital letter sigma. It's a summation sign. It's telling us to add up a bunch of things. I here, this is not the imaginary number I. I is my index, and it's taking on integer values from 1 to n. So my index, go 1, 2, 3, all the way to n. And what we're supposed to do is for each value of the index, we're going to get a term in our sum. And in this case, the term actually is equal to the index. So when the index is 1, we get a term of 1. Plus, when the index is 2, we get a term of 2. Plus, when the index is 3, we get a term of 3. Plus, 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 all the way through to the last term in our sum is going to be our final index, which is n. Okay. And what this formula is doing is it's giving me a shortcut for adding up a bunch of positive integers. So that, for example, if I had the sum as my index goes from 1 to 100 of I, that's going to equal, now in this case my n is 100, so I can simply plug in 100 to this formula. So it would be 100 times 101 over 2, which is just 5,050. That gives me a really fast way of adding up the first 100 integers, a lot faster than just adding them up one at a time. Okay. All right, so that's just a quick review of what this notation means and what this formula allows us to do. Now let's actually tackle the proof. So if I'm using induction, notice the induction axiom is essentially an if-then statement. And I know that the induction axiom is true. So what I need to do is establish that these two hypotheses are true. Once I establish that these two things are true, I get to conclude that my formula is true for all values of n. So I'm going to start with this first one. We call that the base case. The base case is going to be when n is equal to 1. So I need to prove that this formula is valid in that one specific case when n is equal to 1. Now, it's an equation that has a left-hand side and a right-hand side, so I'm just going to simplify what each side of the equation is if n happens to be 1. So the left-hand side would be the sum, as my index goes from 1 to 1. So notice my initial index and my ending index are the same, of I. Well, my index, I start at 1, and I'm done, because I end when I hit my final index of 1, and we simply have 1. So we have just one term. There's nothing that I'm adding to it, but a sum of one term is just that term. So the left-hand side is 1. The right-hand side, I'm going to take this and I'm going to plug in 1 for n. So that would be 1 times 1 plus 1 over 2. That's 1 times 2 over 2, which is 1. Left-hand side equals right-hand side. So the base case holds. So I've established the first of these two hypotheses. Now I need to establish the second hypothesis, and that's a little bit trickier just because that second hypothesis is itself an if-then statement that I need to demonstrate is true. And of course, the way I prove an if-then statement is by supposing the if part. So we call that the induction hypothesis. That's when n is equal to k. So n here is essentially a variable that can take on any positive integer value. K we're letting represent a fixed but unspecified value. So we're saying somewhere for some value of k, this is true. So I'm just going to suppose that the sum as I goes from 1 to k of I is equal to k times k plus 1 over 2. Notice that's the formula that I'm trying to prove, but every single one of the n's got replaced with a k. Okay, so this just says the sum of the first k integers can be calculated by this formula. Okay. So I've supposed the if part here. I need to prove the then part. So I need to consider the sum as k goes from 1, as I goes from 1 to k plus 1, so that my final index is now k plus 1. Okay. When n was equal to k, that was called the induction hypothesis. This is now the induction step. That's when n is equal to k plus 1. Okay. Oops. And I'm considering the sum as I goes from 1 to k plus 1 of I. Okay. Well, I need to show that it's equal to this formula, but when n is replaced with a k plus 1. So I think off to the side here, I'm just going to write that my goal is to get to k plus 1 times k plus 1 plus 1 all over 2. That's what I would get if I replaced n with k plus 1 here. Okay. And somehow I want this to be true because this was true. So I'm going to observe that this, the sum of the first k plus 1 integers, is just the sum of the first k integers plus 1 more. If I'm doing, for example, if k was 5, so k plus 1 was 6, the sum of the first 6 integers, 1 plus 2 plus 3 plus 4 plus 5 plus 6, would be the sum of the first 5, 1 plus 2 plus 3 plus 4 plus 5, plus the last one, 6. Okay. But now, I can say that this, by the induction hypothesis, is equal to k times k plus 1 over 2 plus k plus 1. And now, keeping in mind that this is my goal, I want to have a single fraction with 2 in the denominator. So let's just multiply this by 1 in the form of 2 halves. So I'm going to have a single fraction with 2 in the denominator. And we'll have k times k plus 1 times plus k plus 1 times 2. I'm going to go ahead and factor out that k plus 1. So that's k plus 1 multiplied by, here it's being multiplied by k, plus here it's being multiplied by 2, all over 2. That looks an awful lot like what I want. Let's just really be explicit and observe that that is exactly what I want. This is k plus 1 multiplied by k plus 1 plus 1 all over 2, which is exactly this right-hand side with n replaced with k plus 1. So that's the induction step, showing that the formula holds for k plus 1, and somehow in the process using the fact that the formula held when n was equal to k. So all that's left is for us to state our conclusion. I'm running out of space here, so I'll give myself a little bit of space. And then we can say, thus, the sum as my index goes from 1 to n of I is n times n plus 1 over 2, and that holds for all positive integers n. Excellent.